Everyone, let's take a look at this question. We have a 64-year-old man and he's being evaluated for persistent fever and weakness. He has a history of aortic valve replacement for aortic stenosis, and on physical examination there is a new cardiac murmur with scattered petechiae splinter hemorrhages seen on his extremity. Echocardiogram shows vegetation of one of the aortic valve leaflets and blood cultures grow enterococci. Till now, it is quite evident that the patient has infective endocarditis. So, as a part of patient's treatment, 240 mg of IV gentamicin is started. The pharmacy calculates that in this patient, the volume of distribution, so they have given us the dosage of the drug, 240 mg IV they gave. Volume of distribution was 30 liter, half-life of 4 hours, and demonstrate first order and one compartment kinetics. Now this is also important that it has first order and one compartment kinetics. They are asking us what will be the serum drug concentration just before the next dose 8 hours later. They are asking us the drug concentration in the serum at 8-hour interval. We need to know the formula of VD for this question. Volume of distribution. Volume of distribution is basically the amount of drug that we have given to the patient or the dose of the drug that has been given upon plasma concentration of that drug. Plasma concentration of that drug. Now in this question, if we use this formula, we already know the VD. We already know the amount of drug that has been given, 240 mg. We can just plug in those values and get the plasma concentration. So plasma concentration is going to be 240 milligram divided by 30 liter, which is the volume of distribution, 30 liter. So we get the value of 8 milligram per liter. Now, another thing that has been given in the question is T half-life. T half-life of 4 hours. What is T half-life? The time it would take to reduce the concentration of the drug to 50% of its original value. So in T half-life, which is 4 hours here, it will reduce to 50% or half of its value, which is 4 mg per liter. If we give it another, it would take another half-life of 4 hours to further reduce to half, which is 2 mg per liter. And as simple as that, we get it. What will be the serum drug concentration at 8-hour interval? So at 8-hour interval, that is 2 half-lives have passed, we'll get the serum drug concentration of 2 milligram per liter, and that is our option B here, 2 milligram per liter. Whenever we are trying to give any drug, we want to have optimal antibiotic therapy, optimal drug therapy, especially like in this question, we were dealing with gentamicin. Now gentamicin, if it is like, let's say optimal therapeutic level was not achieved, it would lead to nephrotoxicity, right? So pharmacokinetics becomes very important in these kind of questions. And in this question, we basically had 2-3 terms that became very important. We needed to know about the volume of distribution. We also needed to know about the half-life, and then they mentioned about some first order kinetics. So now I'm going to take some time and explain how all these things interplay and what exactly they are. So first term that we are going to take up is volume of distribution. Now for any drug to like exert its effect, it needs to distribute. It will go into the circulation, and from there it is supposed to go into the target tissues and organs. So we get the first term, which is volume of distribution. It is the volume occupied by the amount of drug in the body relative to its plasma concentration. And we get the formula from here, VD equals to amount of drug in the body upon its plasma drug concentration. Now, distribution, when a drug is distributing from the blood to the tissues and organs, the distribution will depend on drug's properties. A drug has a low VD. A low VD means that the drug is going to be mainly intravascular. its plasma concentration is going to be high. It's going to be highly plasma protein bound. It will be a large charged molecule that prefers to stay intravascularly rather than in the tissues. That's why it has a low VD. And good example would be heparin. Heparin is a very large molecule. So it will stay in the intravascular compartment only. It will increase the plasma drug concentration, making the VD very low. Another example, heparin. Heparin is highly plasma protein bound. Because it is a highly plasma protein bound drug, it is again going to increase the plasma drug concentration and it will have a low VD. Then we have drugs with high VD. High VD means they are the exact opposite of this. They prefer to stay in the tissues, especially fat. They are small lipophilic molecules or substances that are highly bound to the tissue protein. So they preferentially distribute into the tissues. That is why these ones have a high volume of distribution. So when we say that a drug has high volume of distribution, we can see that its plasma drug concentration is going to be low and its volume of distribution is going to be high. The amount of drug in the body, like in the tissue, is also going to be high. In between these two, we get the drugs with medium volume of distribution. When a drug has medium volume of distribution, it is going to stay in the ECF. And high VD drugs, high volume of distribution drugs, were small lipophilic molecules. If we have small hydrophilic molecules, hydrophilic means they won't be able to cross the lipid bilayer that properly because they are hydrophilic. So they will have a medium VD. Then moving on to the other thing, which is clearance. Clearance is the volume of plasma that is cleared of the drug per unit time. And what I want you to note is that between the formula of VD and clearance, the only difference is in the numerator. Here we have the amount of drug in the body and here we have the rate of elimination of drug. So therefore, the formula of clearance we can get by putting in an elimination constant. If we take the volume of distribution and just put in an elimination constant, multiply the two of them, we can again get clearance. When we talk about clearance, clearance is where the concept of first order kinetics, zero order kinetics comes in. Most of our drugs follow first order kinetics. When we say a drug follows first order kinetics, it means that a constant fraction of drug is being eliminated per unit time. That brings us to half-life. The time required to change the amount of drug in the body by half. What will be the time required to change the drug to half of its value? Now, why do we need to take into account half-life in this question is because in first order kinetics, means constant fraction of drug is being eliminated per unit time. If we infuse a drug at a constant rate, it will take around 4 to 5 half-lives. It will take 4 to 5 half-lives in order to reach a steady state. Steady state is when the rate of drug ingestion is equal to the rate of drug elimination. Right? So it takes 4 to 5 half-lives to reach steady state. And another formula for T half-life is given here. It is 0.7 times volume of distribution upon clearance in a first order kinetics. That is why we need to know in that question that, okay, first order kinetics, because the concept of T half-life applies very nicely, especially and only for first order elimination. We can see here, in one half-life, the drug will become 50% of the original value. 2 half-life, it will become 25% of that original value. 3 half-life, it will become 12.5 of that value. And at 4 half-lives, it will become 6.25% of the value. So it will take you 4 to 5 half-lives to reach the steady state. And these were the 3 things: volume of distribution, clearance, half-life, that we needed to know in that question.